Hello everyone. We're presenting a design project for a wearable infant hydration monitoring system for the IEEE VC-ACS 2016. The project was completed by Tala, Jingjiang, Brian, and Ethan for the Biomedical Instrumentation course at North Carolina State University. Dehydration is a complex physical and chemical process which disrupts the homeostasis of the body at both the system and cellular levels. Severe diarrhea, which can be induced by dehydration, is the leading cause of morbidity and mortality in children and infants. Hydration monitors, however, are generally limited to clinical environments and are not currently incorporated in wearable health monitors. Thus, it is our primary objective to provide hydration monitoring at a consumer level with a non-invasive, wearable, bioimpedance-based hydration sensor. Dehydration exists as a continuum of states. However, in clinical assessment, it is brought down to several stages, ranging from mild to severe. It is our goal to measure the dehydration of the test subject such that moderate to severe dehydration may be avoided. Current monitoring techniques include bioimpedance analysis, blood and urine tests, optical techniques, and the conventional pinch test, which tests the elasticity of the skin as a measure of dehydration. The blood and urine test is the most accurate chemical technique. However, it is invasive and requires costly lab. So we have chosen bioimpedance analysis for its non-invasiveness as a way of measuring the impedance of the body as related to the dehydration of the subject. However, it suffers from both environmental and body composition influences. Bioelectrical impedance analysis is a well-documented technique for quantifying body characteristics related to hydration of the body. The body composition can be broken down into the fat-free mass and fat mass. However, we are focused on the total body water in the system, which is a combination of both the intracellular and extracellular water. Advantages to using bioelectrical impedance analysis are that it is safe and invasive, inexpensive, portable, and measurements of hydration may be taken in rapid succession. The theory for a hydration sensor based on bioelectrical impedance analysis is founded on the fundamental principle that the impedance of an isotropic cylindrical conductor is related to its geometry, such as the length and cross-sectional area, as well as the applied signal frequency. From these relationships, we can determine the volume of the cylindrical conductor based on its resistivity, length, and the impedance measured at a given signal frequency. We can extend this theory and compose the human body as a series of these cylindrical conductor components and find that the total body water, a measure of the volume of these cylinders, is related to the square of the body and inversely proportional to the impedance of the measurement.
The wearable system consists of three main components. The conductive electrodes, which are gel electrodes, are wearable transducers. They're connected to the transduction circuitry, which transduce the signal with an impedance analyzer and send the signal over with a microcontroller with a built-in Bluetooth Low Energy. The phone application contains a graphical representation of the data and is shown to the user in graphical formats. In this slide, you can see the proposed and the final design of our system. Our system is built on top of a leg warmer, and the electronics are contained inside a 3D printed enclosure. The gel electrodes are connected to the circuitry with cabling. In this slide, you can see our circuit design more clearly. On the top left, you can see the platform that we use to collect our data with. It's an Analog Devices 5933 evaluation board, which we have replicated the circuit for our final circuit design. You can see the circuit of the 5933 chip, which is an impedance analyzer, in the center of the slide, it has an analog front end, the same thing as the evaluation board, built on the circuitry on the right. You can see the comparison of the circuitry size with a quarter, and the back is also shown. Our system starts with a 5-minute pause to get the electrodes to fully bond to the skin. After this, we collect 20 data points, average them out, and then find the initial impedance value. Using this initial impedance value, we then sample the impedance values at 5-minute intervals and then send the percent difference from this impedance value to the user so that the user can see the data. Our Android application has 3 tabs. The first tab is used to connect the Android application to the circuitry. The second tab shows the data by text, and the third tab shows the data in graphical format. So this is the demo of our infant hydration monitor project. This is a baby leg warmer. For the purposes of this demo, we'll be connecting these 2 leads to simulated resistances. But for the real thing, we connect them to the baby's body with this gel electrode. So our device works with impedance. So based on impedance change at 50 kilohertz range, we predict hydration change. Let me show you some of the device components. If you open up this enclosure here, we have the device. The device has an RF chip over here to compute the values, communicate with the impedance analyzer chip, and send the values to our phone. This is the impedance analyzer chip. There are some analog front-end components. On the back, we have a battery and a battery regulator. Let me connect a simulated impedance value. So this is an initial impedance value that we base our percent changes to. I'll turn on this device.
So the device then do 20 times of measurement to find the reference point. And right now we have an Android app to display the result. First, for the app, we have a connect page, which checks the connectivity of the Bluetooth on the phone. Once it's turned on, we can click scan, which will find the Bluetooth low energy device in the proximity area. We just click connect to connect to our device, and then we go to data, which shows the initial volume, the percent change of the initial volume since you first time you take the measurement. So right now here it shows 0% change because we haven't changed the resistance yet. So right now we're gonna change it, the resistor to 1600 ohm. So we should be expecting a 60% change. So right now we're seeing about 50%, 52%. Oh, we have 64% change, which is about right. On the third tab, we also have a graph which shows your a graphical view of a percent change over time.
For the purposes of this specific video, we had a higher sampling rate or a shorter sampling amount. That's why it ran faster.
As previously mentioned, we use the evaluation board for the bioimpedance circuit to assess dehydration. This is done by assuming that the mean value of the impedance measured at 50 kilohertz is proportional to the inverse of the total body water as predicted by the Watson equation as shown. The figure on the upper left shows the impedance spectrum as a function of time for several measurements of Tala. And as you can see, plotting the impedance at 50 kilohertz as a function of time, we can see a general decrease in his impedance as he consumed water over the course of 3 hours. Using the assumption before that the impedance is inversely proportional to the total body water predicted by the Watson equation, we can see by the figures on the bottom that, in general, as Tala consumed water, is total body water and percent hydration increased. Some of the main conclusions for this work that we need to know is really that bioimpedance is only adequate in measuring percent change in hydration. However, due to changes in resistivity from person to person, it's very difficult using impedance techniques to assess an instantaneous value for total body water. Additionally, another thing that we noticed in our testing is that if we assume linear proportionality, that the changes in total body water measured seem to be much more dramatic than what we would expect. It appears that there might be some nonlinearity with our sensor in that if we assume that the impedance changes more with the square root of the hydration, we get more reasonable results. And that concludes our talk.